any questions, and feel free to stop me at any point in time if anything is confusing or anything like that. Like I said, my name is Michael O'Rourke. I run Pocket Network, and that's my Twitter handle. I like the Twitters. So yeah, Cryptoeconomics 101. Again, we're just going to go over the basics of what it means to build a blockchain, right? And how maybe you could use these concepts to build one yourself or build something on top of another system. So I want to start off with just a definition. And cryptoeconomics is used in building systems that use cryptography to prove properties about messages that happened in the past and economic incentives defined in the system to encourage desired properties into the future. And it's well known that Vitalik Buterin, he kind of coined the word cryptoeconomics. And it's been, the field was really invented in 2009 with Bitcoin. And to kind of dig a little bit deeper into this, cryptography is the really important thing that helps prove who you are online. That's how you're able to say, when I send this Bitcoin, I can prove it is who I said I am, right? And I'll go into that a little bit. And the economic part is how do you make sure that everyone who's acting in the system stays honest and rational. And that's through economic incentives. So it's like put your money where your mouth is. If you participate in this network, you are participating in the economy of this network. So you can even think of it like each blockchain is almost like its own little nation state. And there's a set of incentives and laws that everyone who, if you buy Litecoin, it has its own rules. If you buy Bitcoin, it has its own rules. If you buy Ether, it has its own rules, right? And that goes with any blockchain. And those are the economic incentives and rules that everyone has to abide by. And it's to encourage people. So you can't write in the law how humans act, so you can write incentives in code that make people act certain ways, is kind of the idea. So what is cryptoeconomics? It's cryptography, economics, game theory, distributed systems, computer science. I should have added psychology on here too. All of these things. It's a really broad field, and you need some expertise in all of it to be able to kind of put everything together in a way, or at least some understanding, right? I'm not a math person, but you can still kind of understand these things, right? So, or at least understand how they work. So, first thing I want to do is I'm going to go over the cryptography part of cryptoeconomics. This forms the complete base layer of how all this stuff works, and it all starts with these things called hashes and signatures. A hash is a function. It's a math function. So, if you took algebra, you know what a function is, right? In blockchain world, it's considered a black box. So you put something through the hash function, and it has an output that is completely random, and it's just a gobbledygook set of strings, or a string, right? And this idea of pre-image resistance, so I'm going over the properties of these cryptographic primitives, right? So there's some important properties that that cryptography has that the blockchain uses. And the first one is pre-image resistance. So this idea of pre-image resistance, meaning you put in an input, the hash function is a black box, and it spits out this random string. And the idea being you can't reverse engineer what the input was. This is the idea of pre-image resistance. It's literally impossible to reverse engineer so if I put in my name, Michael O'Rourke, as a string in here, or I put in a photo of a dog or a cat, or any image, anything that can be compiled into ones and zeros, basically. If I put that through a hash function, it's going to come out with this output that is completely random, and it's impossible to reverse engineer what that image or word was. And that's what a basic hash function does. And one of its properties is this idea of pre-image resistance, which makes it impossible to reverse engineer whatever it was before. Another property of hashes is this idea of collision resistance. Those of you who've heard, those of you who understand Bitcoin and the way wallets work, this is the odds of you winning the Powerball, this first one. The odds of you randomly guessing someone else's Bitcoin address is down here. To put it another way, if you pick a grain of sand and you say, what are the odds of me finding this grain of sand in the entire Earth? It's pretty difficult, right? Now, if you take it to this solar system, finding one grain of sand in an entire solar system, Bitcoin is actually harder than that. It's actually if you find one grain of sand in an entire in the Milky Way, in our galaxy. So it's almost impossible. It's literally almost impossible to replicate one of these hash images, right, or one of these hashes. And this idea of collision resistance, meaning you're randomly generating a number, basically, and it's the odds of that number being someone else's are almost impossible. So that's the idea of collision resistance, and that's one of the features of cryptography that Bitcoin uses. And the other one is there's a concept in computer science where it's really hard to it's actually impossible to come up with a truly random number. And in fact, this is actually should be pseudo-random number, but it's random enough to where it's extremely difficult to reverse engineer the idea of a random number. Here I'm using an example of someone finding a block in Bitcoin. So the difficulty in Bitcoin is based on someone generating a hash with a certain amount of leading zeros. Now, the higher the difficulty, the more leading zeros there are, which means the smaller the probability of one of these computers actually finding the right block in Bitcoin. So, and that's them using this idea of random numbers, right? A random number generator to find a block in Bitcoin, because these things are doing, millions of hashes a second. So they're hashing the same thing over and over, hoping for one number. And the randomness is, a certain amount of leading zeros, and the block that finds the one with the correct amount of leading zeros is the one that actually finds the Bitcoin block. So this is the idea, and the idea of hashing anything and using it as a random number is, for example, you can use these bottom things as random numbers for anything. So if you need to randomly pick someone for delegated proof of stake or any kind of system, you can actually do that by using these hash functions. So those are some really important properties that these hash functions have. And leading to that, there's the idea of public and private keys. The best example I can think of for this is the idea of email. You have your public email address and you have your private password. You can log into your Gmail from anywhere around the world, and you can access your email, right? It works the same with crypto. As long as you have your private key private, you can access your wallet from anywhere, right? As long as there's some software that's there for you to be able to do it. You can just input your private key, and it uses the Bitcoin hash function to create or to correlate that with your public key. So what happens is you use a specific, I'm not going to get into the specifics of the types of hash functions, but there's dozens, probably hundreds of them. There's very specific ones that Bitcoin uses and Ethereum and these blockchains. But what happens is when you create an address, it creates a private key and a public key. The public key is for everyone to see, to send crypto to. And your private key is your access to all that. So instead of someone stealing your email, they can steal your money, which is, you want to keep that really, really safe, right? And this is just using those same hash functions that I was using, or that I was talking about. So the public and private keys have those properties of that I was just speaking of. There's three main things you can do with your private key, or to create one, right? So you can generate your keys. This is a standard, programming method that anyone can use. And these are the two really important ones: sign and verify. Signing is the act of signing some message or some set of data with your private keys. So it's like when you sign something with private keys, it actually turns into that really weird-looking hash, right? And only you can prove that, right? So you're saying, hey, I'm going to sign this with my private keys, and I'm going to send my Bitcoin, my one Bitcoin to someone else, right? And you as an individual are going to be, since you control them, you can go ahead and sign that and provide that authorization or that proof to the network that you are the person that did it. Another great part of this is that other people can actually verify. A third party can actually verify that you are who you said you are, which is what miners do. So they're actually verifying private keys based on the expected output of what you said you sent. So that helps avoid things like the double spend problem and stuff like that. So those are kind of like the really important things. And the idea of signing, you can use it for anything. And it's the idea of digital ownership. And you can prove that you own some action or that you did something by signing something with your private keys. So that's a really, really important concept that you can use in just about any cryptoeconomic system, quite literally everyone.
Mike, can I back you up 2 slides real quick?
Yeah.
One more?
Yeah.
When you're mentioning like the public key is kind of your email address and the private key is kind of your password.
Correct.
I definitely get the analogy. I just kind of want to push the point. Yes, but I don't need to give that password to anyone.
Correct. Good point.
I only sign the message with my key, so I never actually give that password.
Correct.
I do the sign instead. That's how it stays secure.
Yes. So in like Google, right, they have your password, right? It might be encrypted, but they still own your password. And thank you for that, Sean. In this case, you personally have your private key, and you're saying, I authorize this transaction, is all it is, right? So I want to go over a couple definitions. So we're going to get into the more distributed systems part of this talk. Distributed systems, by the way, is like when I make a post on Facebook, how quickly do my friends see my post? Facebook has servers all around the world, right? How do they decide who sees it first and how quickly? And how does that get propagated throughout Facebook's networks? Or Amazon, with their load balancing for Amazon Web Services, or any social network at scale, or any website that uses scale, with the database has this idea of consensus, where you have a bunch of people putting in a bunch of data, and how does these databases know which data is correct? is kind of a big problem with distributed systems, things like that. So, and you're going to hear this word consensus all the time. You probably already have, right? So yeah, consensus problem requires agreement among a number of processes or agents. And agents is another word for nodes in blockchain world, for a single data value. Some of the processes or agents may fail or be unreliable in other ways. So consensus protocols must be fault tolerant or resilient. The processes must be somehow put forth to their candidate values, communicate with one another, and agree on a single consensus value. So a single consensus value is one single source of truth, which is a blockchain, right? So what blockchains do is they find consensus on all the transactions that have happened, and they use that by different kind of consensus protocols. They must be fault tolerant, meaning, which I'll go into in a second. Well, let's go into fault tolerant, actually. So fault tolerant. Bitcoin, right, or miners, any kind of proof of work based system allows any person with a GPU or an ASIC to kind of come into the system and come out of the system, right? To be able to go in and out with while still keeping the single source of truth is basically fault tolerance. It allows the system to continue operating in the event of a failure. So someone didn't propagate a message. So I'm a Bitcoin node and someone sent a transaction through me. Did it get propagated? Is it fault tolerant? That's kind of how it works. So yeah. So the idea is this is really important in really mission critical systems. So I'll go into a little bit more, but systems like SpaceX, NASA, they use fault-tolerant systems to keep people safe. And this is another thing I want to talk about, and this idea of liveness and safety in blockchains. And I'm going to try to keep this theme going of liveness and safety to the consensus protocols when I explain them. But this came from something called the FLP impossibility result, which was in 1985, actually. This result was done by some computer scientists. And they basically saying something can be fault tolerant, but it can't be live and safe at the same time. Safety is basically guarantees that nothing bad happens, while liveness guarantees that something good will eventually happen. So what does that mean in the context of a blockchain? I'll get into it a little bit later, but basically Bitcoin, their consensus protocol is prioritizes liveness, meaning there can be lots of forks within the Bitcoin protocol, but all the miners agree on that the longest chain is the correct chain, right? So this is the idea of liveness, where there could be lots of incorrect versions of it at the beginning, but by the end of it, eventually, everyone agrees that the longest chain is the correct chain. The idea of safety actually is the opposite. So whereas in Bitcoin there's a bunch of forks. Those of you who's here familiar with like Casper, with the Casper proof of stake mechanism. That's another, which I'll go into in a second, but that's the other consensus protocol that prioritizes safety. So whereas in Bitcoin there's a bunch of forks, all the validators or the nodes in Ethereum or Casper all have to agree on one version of the chain. So that's the idea of safety. So there's only one agreement on that. And that's kind of, I'll go into it in a little bit, but yeah, those are kind of the two things. And you'll see this, if you do any research on fault tolerance and in the context of blockchains, you'll see these words thrown around a lot, liveness and safety. It took me a while to kind of wrap my head around it, but it's kind of like in computer science, there's trade-offs for everything. And this is one of these trade-offs, is it can either be live or safe. It can't be both. Or it can be bad at one and good at the other. So I'm just going to go over a history of kind of the major breakthroughs in this idea of consensus algorithms. And these are all up until proof of work and Nakamoto consensus. This is all in context of distributed systems. So you have Google growing extremely fast in 1996, 1997. They have this big problem where how do they keep all the integrity of their data safe, right? How do they keep everything, well, this is a big problem with any big tech company, actually. But it started, actually, you could say that the history started back in when the internet was created, where someone had to create a fault-tolerant way to get data from one internet node to the other, right? So packet switching is a fault-tolerant form of sending data, right? So you can send data through, in little packets through the different protocols, TCP/IP or HTTP, and you can be sure that it reaches the intended recipient in a fault-tolerant way, because other nodes potentially could fall down. What if they disconnect? What if, stuff happens, right? So the idea is to be able to send data and prove data in a fault-tolerant manner. So first thing I'm going to talk about is the Byzantine generals problem. If you've read about Bitcoin, this is one of the first things that Satoshi Nakamoto references in his white paper. And this basically is an agreement problem. And this was described by Leslie Lamport in a paper in 1982, this idea of the Byzantine generals problem. And the idea is you have a group of generals way back when, and they're commanding an army, and you don't know which generals are honest, and you don't know which messengers are honest. And the idea is how do you coordinate? And the idea is they either have to all retreat together or all attack together, else the attack will get foiled and everyone will die, right? So how do you do that knowing that there are dishonest people in the system, right? It's a computer science problem, actually. With this paper that Leslie Lamport, where they talked about the Byzantine generals problem, they solved this idea. So you'll hear BFT a lot if you look into like really consensus algorithms and things like that. You'll hear like, oh, this is Byzantine, or this is fault tolerant. This is where it actually comes from, is this idea of the Byzantine generals problem. And this is the problem that they described, and they have a consensus algorithm that says, hey, this is how we solve it. And this is done through the idea of signing messages with your cryptographic signature. So this is where you're really starting to use the cryptography to sign with your private keys to say, hey, I am who I say I am, and this is the decision that I'm making in the context of this system. So if you are dishonest, you can immediately be singled out, if you will. So Paxos. Paxos was a protocol published in 1989. It was named after a fictional legislative consensus system used on the Paxos island in Greece. And the best way I could describe Paxos simply is like it's like marriage. So you have the what's the name of the person who says you get married? The minister? Yes. So you have the minister says, "Are you going to get married?" And the two partners say, "I do, I do." And that they've just reached consensus by saying, "I do," right? Now, who approves that? The minister does. So that's kind of a really simple way of a consensus protocol, but with humans, right? Now, this is a little bit more complicated. So you have someone who suggests some kind of change, and they're going to request whether I can get it or not. They say yes, and if yes, then the arbiter says this is what gets put into the database, basically. It's kind of, it's based on simple majority, so whoever says that the most is right, or whoever votes that this data is correct as of 51% is the one who says that the data is correct in this case. And this is a Paxos program, and this is 1989. So people have been really thinking about this for a while. So this led to 4 major consensus algorithms, one before Bitcoin was created. And these are the 4 major ones used today. That all the research that happens today that you read about, proof of work, proof of stake, delegated proof of stake, Hyperledger, any one of these systems are using one of these 4, and that's it. So this is a really new industry, and people are doing tons of research on this stuff. First one is PBFT, Practical Byzantine Fault Tolerance, which is the Paxos algorithm, just with one extra step. And this extra step is actually the pre-prepare step. So, and it adds this idea, so who's familiar with like a federated system, like a blockchain federated system, right? Like EOS is federated, Hyperledger is federated. So you have designated trusted nodes or servers that are saying we are going to state what the data is at any given time, right? They're using some version of PBFT, every single one of them. So you can see why PBFT is considered more efficient, because you're using trusted nodes and you don't actually have the need to propagate those messages to everyone in the network, right? So this is an idea of PBFT, Hyperledger uses it, and a bunch of the other ones, right? So also Stellar uses it, and Ripple uses it actually. So this is the generals in this case are the federated nodes, and the Byzantine general and the Byzantine generals problem. So as long as 50%, 51% say this is correct, then the state change goes through. And the idea is for this model to really work, the greater amount of nodes, because it takes one, actually it's not, I'm sorry, it's actually 1/3, not 67%. So as long as there's 1/3, less than 1/3 of malicious nodes in the network, everything works. The idea is that the more nodes there are, the harder it is to break. So that's how federated systems work. And proof of stake, what's also known as the Nakamoto consensus, which is basically saying the longest chain is the right chain. And this is what I mean by liveness. This happens every day. Like there's forks, little mini forks that happen in Bitcoin every day where people are mining for nothing for a short amount of time. It might be 1 block, might be 2 blocks, might be 3 blocks, who knows. But they're mining on a fork of Bitcoin. That's not the real Bitcoin. So these are these small, and this is considered wasted work in the Bitcoin ecosystem. But this is also the idea of liveness, where eventually all the nodes will get onto the right chain, because I might be some node here, and I'm mining, and then I realize, oh crap, I'm on the wrong chain. Let me go mine on the right chain. So eventually, after some amount of time, everyone will be on the right chain. Else they're just wasting energy for no reason, right? So they are incentivized through Bitcoin, through earning Bitcoin, to be mining on the right chain, because otherwise they're just wasting their energy. Yes? I'm sorry? I said proof of stake. Proof of work, sorry. So proof of work is the Nakamoto consensus, right? And before I get to proof of stake, actually, there was so this idea of the longest chain is really the Nakamoto consensus. Shortly after Bitcoin, like 3 years, those of you who have been around for a while, you probably heard of Peercoin or NXT. Some of these other these are the first proof of stake protocols. So people are mining, but through stake instead. And it was actually the same exact kind of consensus as Bitcoin, where this idea of they still prioritized liveness over safety, right? Because part of the problem, and by creating these first versions of proof of stake, some attack vectors got created. Like people found out some important attack vectors. One of them is called the long-range attack, and the other one's called the nothing at stake problem. And these were important attack vectors that eventually made these cryptos, Peercoin and XT, actually worthless because they kind of they were really easy to take over kind of attack vectors. So that was the first generation of the proof of stake protocols, was these Nakamoto consensus proof of stake protocols. The next version are what we see today. So Casper, and is anyone familiar with Tendermint? Is familiar with Tendermint? Cosmos? There's no Cosmos. Tendermint is the other proof of stake protocol that is BFT consensus. So it's Byzantine fault tolerant consensus, but it's proof of stake. So what I mean by that, if you see in this image, there's just one chain. And the right chain is the one where there are 2/3 or 3/4 votes. So the validators in this case are voting on the blocks instead of kind of selfishly mining, and I could be on my own fork. In this case, there's only one chain, and they are all, the right chain is the one that gets voted on. So this is the idea of safety. There's no kind of forks that happen in this case. And if I'm not on this right chain, I'm going to get slashed. I'm going to get burned immediately, actually. So that incentivizes everyone to be voting on the right chain. So this is the idea of safety, where you're prioritizing the correct one right away, as opposed to eventually getting to the correct one over some period of time. And that there's different trade-offs with that. And it's done through kind of like a like a voting process. It's like I see one block, I see another block. I'm going to vote on this one. If I'm wrong, then I get burned. If I'm right, then I continue on as I would, right? And yeah, that's kind of proof of stake. And those are the two things between safety and liveness. And then we have, lastly, delegated proof of stake, which was BitShares. EOS Tezos is also delegated proof of stake. Delegated proof of stake it uses Nakamoto consensus, but you're staking coins on behalf. So because you're trusting, it's a mix between Nakamoto consensus and PBFT. So the PBFT part are the federated nodes, where you're delegating your stake to. So in EOS, that's 21 nodes that you're trusting, right? In Cosmos, it's I want to say it's 100 or 300 or something like that. But it's actually, and these nodes are using Nakamoto consensus, but instead of anyone kind of being able to participate like you would in mining, you are there's only a few chosen nodes in this case. So it's a mix, actually. It's a hybrid. Also, with delegated proof of stake, if you go back to the previous triangle, it sacrifices decentralization for an improvement in both safety and liveness, actually. So there's a trade-off in that too. So the idea is, the big thing about delegated proof of stake is that it's quick, the high throughput, high transactions per second, and it's trustworthy. But you have to be able to, or it's decentralized, but it's not really, right? It's just, the less decentralized it is, the more throughput you can have, because there's less consensus among nodes needed, right? It takes a shorter amount of time to reach 51% consensus over 21 nodes than it would, the 30,000 Bitcoin miners in the world, right? Or whatever that number is, right? So how can people use all this stuff, right? I'm going to go over a few ways that people are using things like signing, cryptography, proof of stake, delegated proof of stake, and building simple systems and a little bit more complicated systems on top of these existing ones. So first big one is blockchain scaling.
That previous slide is Lightning, right?
Yeah, Lightning Network and state channels.
But that ain't spelled right.
Lightning. Oh, did I spell it wrong?
I think it's spelled that way. It is.
Huh?
I think that's like caution.
Okay.
Yeah. Yeah, so the first parts I'm going to go over Lightning and state channels and sidechains and plasma. So, state channels. State channels are best described as a cryptographic bar tab. So when I go to a bar, I give them my credit card, and I do a bunch of swipes. I spin up, I get a $100 bar tab that night. It doesn't clear until the next day or a couple days after, right? State channels are similar, except it's like, or a debit card in this case, except you have to have, it's a two-way connection between two parties. So you have to prove that you have, let's say, 100 Bitcoin, and the other person has to prove they have 100 Bitcoin, and they put them in Bitcoin, it's a specific address. In Ethereum, it's a smart contract, and they're saying, I'm approving half a Bitcoin, I'm approving 1 Bitcoin, and then once that channel is closed, it all settles onto the main chain. And this is using quite literally the cryptographic primitives that I talked about earlier that are saying, hey, I'm going to prove I own this amount of Bitcoin, and I'm going to send it to some address, right? And I'm going to make cryptographic signatures spending this Bitcoin over the course of time. So this example is using electric vehicles and earning and using crypto, right, as microtransactions. Another one, has anyone heard of Spankchain? It's like a cam girl site. It's actually a working state channel implementation, believe it or not. So you kind of deposit a little bit of ether or their Spank token, and it's kind of debits as you decide to tip the cam girls actually, and it's an interesting use of it, right? So this is a really big scaling solution. The idea is that you can send as many transactions as you want because it's over the internet. It's not all directly put on the blockchain, right? It's like you have 10,000 transactions and it all settles after the end of the tab or the end of the night or whatever it is. And that's using these cryptographic primitives. So it's pretty cool. Plasma. Plasma or sidechains. If you're familiar with those, the idea is you have a root chain, in this case Ethereum, and you lock up, let's say, a bunch of tokens or a bunch of ether on some block on Ethereum. And you create an equal amount of those tokens on a chain on top of it, right? So you're putting this, in Ethereum's case, a bunch of tokens in a smart contract by cryptographically signing it and saying, I'm proving that I own these keys, therefore I have them on the other blockchain, on some other address, right? And this is another scaling solution for these kind of primitives. And the idea is, if you have a bad actor in one of these systems, it automatically collapses down to the main chain. So it provides this really interesting security, and it's a legitimate scaling solution. In fact, there's a company called Loom right now that's a gaming platform that's actually live right now on Ethereum that's using a plasma chain. So people, and this works the same way with Bitcoin too. Although it's a little bit more difficult with Bitcoin, but it works the same way. There's a project called RSK that allows you to do smart contracts because they built a side chain on top of Bitcoin that basically creates the Bitcoin that you locked up, creates coins on the other side, and then you can actually have actual smart contracts, really general smart contracts like you would on Ethereum, but on Bitcoin. And that's all using cryptography. All of it's using cryptography. So using like simple incentive systems. There's a really cool project called LivePeer, which is decentralized video transcoding. So I want to broadcast like a live stream like people do on Twitch or on my iPhone or something. That data gets sent to some transcoders. So these people are running really specialized software on like Amazon Web Services or on their own home or something like that. But they get chosen by other individuals in the network actually staking on their behalf. So There's only maybe like 10 or 15 of them right now. The idea is that there's more, but the idea being I'm staking on your behalf. You're going to transcode honestly. If you are not transcoding honestly, or if you're serving bad data, you get slashed. You get your tokens burned, or I'm going to remove my stake and find an honest transcoder, or using incentive systems like the transcoders can decide to give out 10% of their profits to the people who stake on their behalf. So these are using economic incentives to say, hey, stake on my behalf, and I'll transcode for you, and I'll give you 10% of my profits, kind of a thing. So that staking is just it's a staking, by the way, is saying I'm promising you, I'm staking my tokens on your behalf. So I keep them myself, but it's like delegates in the U.S. actually voting. So bigger states have more delegates, right? Higher population states, I think. In this case, more money, more delegates, more votes, more power, actually, which is a big problem with delegated proof-of-stake systems as well. Because there's this whole idea of centralization and, the rich get richer kind of a thing.
Is that what Steemit does?
Yes. Yeah, from my understanding, there's just a few whales that really kind of control Steemit,
Yeah.
right? So, yeah, and that's kind of the big trade-off with delegated proof-of-stake. And that's the thing that's actually a concern with proof-of-stake as well. So that's why you heard about the DAO hack, 2 years ago in Ethereum, and Ethereum did that hard fork because one person siphoned, I think it was almost 14% of all Ether at that point in time. And if you're going to move to a proof-of-stake system, having 14% of all Ether it's a really bad thing. So part of their goal has been to kind of spread out to as many people as possible, to have as many nodes as possible who can credibly stake in the system. Token-curated registries. These are really interesting. These are using economic incentives to ensure the right data. In this case, this is a website called Crypto Against Humanity. It's live. It's actually on testnet right now. And the idea is you can buy cards with Ether. These, I don't know, has everyone here played Cards Against Humanity? So you have the black card, and then the idea is you vote one of these, and the highest voted one is the funniest one, right? So you can see the price here at 0.195, but really the prices start at like 0.005. So if I vote on like a funny card and other people find it funny, I actually stake my coins on their behalf, on that card's behalf. And when I do that, the price goes up. There's an algorithm that says the price goes up. So it's an interesting way to order content. Imagine this with like Reddit or something. People staking to, instead of just upvote spamming or any kind of social network, you're staking to say this content is better, right? Or imagine journalists staking tokens on their behalf to have articles that are provably fact-checked, right? You can have really interesting incentive models with things like that, right? And another simple one is non-fungible tokens. If you're not familiar with the term fungible and non-fungible, fungible is $1 always equals $1, or 1 Bitcoin always equals 1 Bitcoin. Non-fungible would be like one cow. You have two cows, but they weigh differently and they have different skin colors and everything, right? That cow is not worth the same as the other cow, whether it be weight or quality of meat, anything, right? So those cows are non-fungible, meaning one cow does not equal the same cow. There's these really interesting tokens that are called non-fungible tokens. If you've heard of CryptoKitties, each CryptoKitty is unique. Well, there's a fun game talking of incentives where you can burn a CryptoKitty where your crypto dragon eats the CryptoKitty and it gets some extra power. And these are done through cryptographic primitives. I mean, you're just signing saying, hey, I'm going to burn this kitty, delete it forever, but I'm going to get a cool dragon, a powerful dragon in return, kind of a thing. So, I mean, these are really simple, fun incentive systems that are all done through cryptography and the blockchain. And what's cool is that you can do this because the consensus algorithms of Ethereum, so proof of stake, proof of work, even PBFT and delegated proof of stake, they all find consensus on the fact when I choose to burn this CryptoKitty, right? And that's all done for me, so I don't even have to think about it, actually, which is nice. And I can think about the economic incentives and the fun games that I can use to build, with non-fungibles and things like that. And you can imagine non-fungibles, with property. Imagine being able to own, 1% of a property, of a commercial property or something like that, and getting some royalties or dividends based on the income of that property or something like that. A lot of people are really excited for non-fungibles, NFTs. So yeah, and that's really it. Hopefully that was somewhat clear. I have a bunch of resources. So it's a rabbit hole. I mean, like the papers, it's really heady and deep, and I'd recommend this last one here, has like from beginner to expert level stuff. So if you want to look into this stuff, yeah, this is just, I mean, you could do a PhD in all this stuff, to be honest. And I just want to try to give you an idea of the framework in which people the experts think about this stuff. So yeah, that's it. Thank you, guys. Any questions?
Who are L4 Ventures?
They are a venture